Sampling-based planners. Explicit geometry-based planners such as VGraph and Voronoi are very impractical in high-dimensional spaces. It's too hard to compute them. You can't get exact solutions with complex geometries. It's provably exponential. And sampling-based planners can often create plans in high-dimensional spaces sufficiently. We'll see how that works, okay? So the idea here is rather than compute the collision-free space explicitly, we're going to sample it. So we don't have to worry about exact positions. We just have to worry about, are we in a place that's okay? So the idea is to generate random configurations of the robot in its configuration space. And once we generate this random configuration, we'll check to see if it's in the free space or it is a member of C obstacles, which means we can't go there. So this is how the samplings work. And what we'll do is we'll try to find n, which is some arbitrary number of collision-free configurations, and link them into a graph. And once we have a graph, we know we can do graph search to find the path. This method uses fast collision detection, having full knowledge of the obstacle set. And the collision detection is a separate module which can be application and robot specific. So if you have a better collision detector or a special one for your application, that works fine. There are different approaches to this problem. One is a single query approach, and the other is a multi-query approach. Single is there a path from configuration to configuration B which are given? Or multiple, is there a path between any two arbitrary configurations in space? So we'll look at both ideas. So one other thing we want to talk about with sampling-based planners is what's the idea of completeness. A complete planner always answers a path planning query correctly in bounded time, including if there is a path at all. A probabilistic complete planner is if a solution exists, this planner will eventually find it using denser and denser random sampling. But you may have to sample for a very long time to cover the whole space. There's also the idea of a resolution complete planner, which is the same as the above, but based on a deterministic sampling, e.g. sampling on a fixed grid. So at the resolution of the grid, you can sample every possible place, and then you'll know the answer to your question. So let's take a look at the first of these probabilistic planners, which is called a PRM, the probabilistic roadmap planner. So the roadmap is a graph G with vertices and edges. A robot configuration, we'll call it Q and Q free, which same as the C space free, is a vertex. An edge between Q1 and Q2 implies a collision-free path between these robot configurations. And again, we need to have a local planner to get this, to do the planning between these two small configurations. We also need a metric to find the distance between configurations. So we want to find the distance between two configurations. And for example, we might use the Euclidean distance if it's a point robot to see where the neighbors are. So what we're going to do is use coarse sampling with the nodes and fine sampling with the edges, and we'll show this in a graph in a minute. So collision-free vertices and edges form a roadmap in Q-free, which is the probabilistic roadmap. So let's see how we can build one of these. Initially, we have an empty roadmap graph G. And a robot configuration Q is randomly chosen. If this configuration Q is in the free space, then we add it to the graph. And we repeat this until n vertices are chosen. So now we have a graph with n collision-free vertices in some space. And for each vertex Q, we select k nearest neighbors, and k is a parameter, typically a small number of nearest neighbors to hook up with. A local planner tries to connect Q to its neighbor Q prime, which was gotten from the nearest neighbors algorithm. And if the connect is successful, i.e. it's collision-free local path, then we add that edge Q prime to the graph. So here's an example that we can see. We have a 2D planar environment with obstacles. Here we do a randomly sampling of the C space for n collision-free configurations. And you'll notice that some of these samples actually are in collision, in red inside of these white objects, which are the obstacles. And so we're going to reject those. So the first thing we'll do when we get a configuration, we check to see if it's in free space or it's not. And if it isn't, then we throw it away. So basically we're left with a bunch of collision-free nodes, okay? And then we try to link each of those vertices, these configurations, in the free space with their k nearest neighbors. Okay, so here you can see how we're building this graph. From each point, which is a configuration in free space, we find neighbors that are close by and connect up to them with an edge. And from that, we can build this graph, which is now what we call a roadmap. Now, when we have the roadmap, if we want to do an arbitrary query, we take a start and a goal position configuration, and all we have to do is get onto the roadmap, and then we can use graph search to find the shortest path. So the start and goal use the same kind of idea. They find the nearest neighbor, try to connect up to it with a local planner, and then once they're on the roadmap, they can then do graph search to find the shortest path. So as you see here, once we connect start and goal to the roadmap, then we can use A-star search to find the shortest path. And again, it handles multiple queries. So once you're on the roadmap, you can find a path. All you have to do is have a start and a goal that finds the position on the roadmap. And this is why you want to sample the space entirely, so you have the ability to go from any place to any other place. There's a problem sometimes with this, and that is the graph may not be fully connected. So we assume that there's a connection between any two vertices on this graph. That's a fully connected graph, but there's no guarantee that that will happen. So in fact, some of these edges, as you can see, may go away, never be there. So in this case, when we built the PRM, we have a bipartite graph. It's not connected. So when I go on the start and goal, I can't reach them. So what do we do to solve this problem? What we can do is denser sampling, more and closer neighbors, to try to make sure that we hook up between any two arbitrary positions, okay? And there are very simple graph search algorithms which will let you tell you if a graph is connected. So you can check for that ahead of time before you actually try to use the planner. So there are details to these planners that we want to talk about. So the first is choosing configurations. We talked about using a random sampling of the entire C-space to pick out these collision-free nodes, and we pick some arbitrary number of them n to cover the space. However, the collision-free areas are kind of easy to navigate. So you have a big free space. You don't need a lot of samples because you can just go anywhere you want to go. You don't need a lot of samples. However, collision regions are where the planner needs to find denser samples. These are tight navigation areas where there are very small changes in configuration can cause collision. So the idea is to use an obstacle-based PRM, OBPRM, which tries to find places where you want to sample denser. So for example, if you find a configuration queue which is in collision, which is in the obstacle set, then you resample in that vicinity of the collision to find a safe configuration nearby. So you just choose a random direction in a small distance from where you had the collision at Q to generate another nearby sample, hopefully in Q free. And this biases the sampling to regions where collisions are likely, which is where you have the most problem in your planner, where there's going to be tight navigation areas. Another thing we want to talk about is finding nearest neighbors. So at each point after we get these n configurations in the graph, we have to find the nearest neighbors. And the brute force search cost is order n, it's naive search, which if n is small is not going to kill you. But if n is large, then you need a faster method. And we can use something like a KD tree, which is a decomposition of dimensions by splitting into two regions alternating each dimension. And we'll show you an example of that in a minute. So it's basically a rectangular decomposition of space. The search is fast and efficient, and the cost is order square root of n for the dimension d equals 2. This is a KD tree, okay? So on the left we have some points in the plane, and what we want to do is put them into the KD tree such that we can do queries on this tree very efficiently to find neighbors and range searches to find a group of neighbors in a certain range. So you can see what we do here is we're going to at the root of the tree we have this node 5276, which is actually the midpoint of all the x values. So you can see that everything on the left branch of the tree, okay, has an x value less than 52. So all those 27, 41, 12, 28, 40, 95, 212, 50, 50, they're all less than that. And on the other side of the tree, the right branch, we have x values which are greater than 52, 70, 71, 54, 10, 62, in the x dimension. So basically that's equivalent to the line you see through 5276, that vertical line in the left-hand part. At the next level, as we go down each level, we alternate splitting on the x and the y dimensions. The next level, we split on y. So on the left branch of the tree, where we have 5276, we go down to 2741, and now we're going to do a split at that on the y dimension, okay? And you can see that we try to split in the middle of the region, so we have as many above and below as we have. So 2741, you'll see that everything on the left part of the graph of the tree from 2741, you can see that everything has a y value which is less than 41. On the right, you have everything which is greater than 41. And you keep doing this recursively down all the levels of the tree, and you can see that the tree has a depth of log n, and it's easy to do searches to find things that are nearest neighbor here. So this is a trick that you should know about. It works also in n dimensions, so if you have 3D, it's a very efficient, fast way to do query searches in many dimensions. How about the local planner? We haven't talked about that. We used to find collision-free paths between nearby nodes. So once we get two nodes, we have to go, can we connect them up with a path? And this is where the local planner works. And it's also used to connect the start and goal to the roadmap. It's called frequently and needs to be efficient. There are two ways to do this. One is called incremental. So if you see on the left, you see a bunch of obstacles, a Q prime and a Q double prime. And the local planner says, can we get between these two configurations, which are usually very close to each other. So you just have to sample along that line and do some interpolation. And you can see here we just go by some arbitrary step size, change the configuration. If you think of joint angles, we're changing the joint angles between theta 1 to theta 2 in some kind of small step sizes and seeing if that causes a collision. And we'll do that sequentially, which is why this is called incremental. You can also do it with the subdivision approach, which is the one on the right, in which basically if you have two configurations, Q and Q prime, you kind of want to guess that, well, in the middle would be the worst place where they wouldn't be the same. So try sampling the middle first, see if it's in collision, and if it is, then you've got a win right off the bat. But if not, then you can recursively do the same thing with each of the two parts of the segment you have by subdividing it recursively into smaller and smaller groups. And again, you eventually will check the same amount of space as with the individual, the incremental method, but it may be more efficient. Okay, we not only have to have the ability to find the nearest neighbor, but we have to have a distance between two configurations. So take a look at these robots and say, is configuration Q in the middle closer, in quotes, to Q1 or Q2? How can we measure that, okay? And we need to have a distance metric between two configurations. Ideally, the distance between two configurations in 3D is the swept volume of the robot as it moves between configurations Q and Q prime. And that's very difficult to compute, especially as you can see with all these degrees of freedom. So what can we do? Well, each configuration is a vector of joint angles. And one possible metric is just take the sum of the joint angle differences. So for this 20, 30 degree freedom robot, we just say, what are the differences in the joint angles, sum up, and take the squared difference, and that's the metric. Well, it doesn't really work well. It first of all ignores movement, translation, and rotation of the robot. So basically, this assumes the robot hasn't moved, it just moved joints, okay, and it hasn't moved in space, okay. And secondly, some joints are higher importance than others. For example, you don't really care too much if the fingers move, but you may care a lot if a leg or a hand moves. So this distance function is not trivial to compute. So what can we do for an articulated robot like this with many joints? Well, one method is to choose a set of p points on the robot and concatenate them into a vector. And the vector of size p times d, d is the dimension of the workspace. So in this thing, this is a regular robot in normal space. So what we'll do is we'll just take a set of 3D points which are sampled on the object. So we may take a point on the top of the head, a point on the end of the hand, a point on the leg, and we can take as many as we want that are identifiable and create a large vector, okay? And we'll call that a sample. And the sample for that configuration Q is a vector of p points transformed by the translation and rotation that is configuration Q. So basically, all these points have a reference point on the body, and so as we know that the body itself has moved by a translation rotation, then we just have to transform each of those points with that translation rotation to create this larger vector of transform points, which is called sample Q. And we can do the same thing for another configuration Q prime. And from that we get a 3D distance, which is the Euclidean distance between the three p vectors, okay? And we'll call that this distance, the distance between these two samples that have been transformed by their respective translations and rotations on the designated points which we've sampled on this articulated robot. Now for a rigid robot, even though it's in 3D, you just have to choose 2 points of maximal extent, because they can kind of serve as the sampling that will say how much this robot has worked, and we'll show you an example of that. So here's a 6 degree of freedom path planning example. So we have this kind of, not articulated, but a rigid object which has a number of parts, and we have to get it through this small hole in this wall. So the robot is a rigid non-convex object in 3 space. The obstacle is a solid wall with a small opening, and you can see this is a fairly interesting and tough path planning problem because there's no obvious solution to it. And the configuration of the solid object is Q, which is translation and rotation, so it has a position in space, x, y, z, and a rotation about the axes of x, y, z. So we can find the random configuration for our roadmap by just choosing translation x, y, z, so that's one of the parts of this configuration, but we have to worry about the orientation too. So we choose a random axis and an angle of rotation about that axis for the rotation. So when we specify a node in the PRM, we're specifying a translation and a rotation, okay, which is the configuration space of this object. And the distance measure uses the 2 extreme points on the object, P1 and P2, which will be transformed by those translations and rotations. And so if we take the distance between P1 and P1 prime and P2 and P2 prime, that will be our metric to see when things are close. And why do we have to know if things are close? Because we have to find the nearest neighbors in our roadmap to move to configuration to configuration. And the local planner will check for collision between 2 configurations, Q1 and Q2, by interpolating along the 3D translation. So each one of them has a translation. We can interpolate along that, and we can interpolate the rotation. So there's a rotation between the 2 different orientations, and we can just interpolate along those. So that's what the local planner will do. So once we find nodes which are fairly close to each other, the local planner will check them more finely. So here you can see an example of the kinds of things that happen. You get a path, and eventually you'll be able to get this through here because you've sampled densely enough to find configurations which are close enough and not in collision.